IBESS, Atmospheric Systems and Pollution Management Part 6, will examine the formation of photochemical smog, a pollution problem that extends from burning fossil fuels and, in some circumstances, deforestation and the burning of vegetation associated with deforestation. As well, we will evaluate methods to reduce smog. The significant ideas are, and there are four, the combustion of fossil fuel produces primary pollutants that may generate secondary pollutants and lead to photochemical smog, the levels of which can vary by topography, population density, and climate. Secondly, photochemical smog has significant impacts on societies and living systems. Thirdly, photochemical smog can be reduced by decreasing human reliance on fossil fuels. And lastly, pollution management strategies can be applied at different levels. Here is the outline of all the available movies in the unit called Atmospheric Systems and Pollution Management. Use this outline to find the movie you need for review. This movie is focused here. Photochemical smog is a chronic pollution problem in the troposphere of urban areas. Smog results from fossil fuel combustion. Smog includes an important secondary pollutant, tropospheric ozone. Be sure you distinguish tropospheric ozone from stratospheric ozone. The respective status of tropospheric ozone and stratospheric ozone to societies is sharply different. Here are two IB syllabus statements that I've covered before but have relevance here. Most reactions connected to living things occur in the inner layers of the atmosphere, the troposphere and the stratosphere. Human activities change the concentration of atmospheric gases, such as ozone, carbon dioxide, and water vapor, which have significant effects on ecosystems. Smog is a troposphere pollution problem. Tropospheric ozone should be distinguished from stratospheric ozone. Tropospheric ozone, a secondary pollutant that is a part of smog, is harmful to living organisms. Stratospheric ozone absorbs dangerous high-energy UV wavelengths, thus protecting living organisms from those wavelengths. Work on distinguishing the relative impact of ozone in the stratosphere and in the troposphere. A reminder, pollution is any substance added to air, water, or soil that threatens the health, survival, or activities of living organisms. And if we can clearly identify the source of the pollution, as we can in this image, it's known as a point source pollution. Photochemical smog, the subject of this movie, is an urban pollution problem. Keep this in mind. Smog is not a pollution problem found in areas far from cities. Smog forms in places with high population densities. Photochemical smog results from point source and non-point source pollution. Here is an image of urban smog in a city, a location with a high population density. The combustion of fossil fuel results in primary pollutants. Primary pollutants, under the influence of UV light, high-intensity sunshine, transform to secondary pollutants, including tropospheric ozone. The role of high levels of sunlight in forming the secondary pollutants of smog is the reason we prefer to use the term photochemical smog. Smog can also result when forests are cut and burned, resulting in high levels of gases that blow into urban areas. Here is an image of deforestation with subsequent burning of vegetation in Indonesia on the island of Sumatra in 2013. You can see how the gases from the burning of the forests is blowing over Singapore and Kuala Lumpur in Malaysia. Here are images of smog in Kuala Lumpur, Malaysia in 2013, when burning forests on Sumatra, Indonesia, resulted in primary pollutants that reached Kuala Lumpur by the wind. Once the pollutants reached Kuala Lumpur, high levels of light transformed the pollutants into secondary pollutants, smog. Photochemical smog originates from the combustion of fossil fuels and deforestation in combination with the burning of vegetation. Both processes release primary pollutants, and under the influence of UV light, the primary pollutants are transformed to secondary pollutants, among them tropospheric ozone. Before I continue, I need to remind you that smog is a troposphere pollution problem. The pollution problem is in the first layer of the atmosphere, the troposphere. You might be saying to yourself, of course, but it's important for me to repeat this idea because you need to distinguish the relative impact of tropospheric ozone and stratospheric ozone. Be thoughtful and pay close attention. Also notice in this image the high density of people and the combustion of fossil fuels. Both high population densities and fossil fuel combustion are relevant to smog formation. Here are the relevant IB syllabus statements. Smog is a complex mixture of primary and secondary pollutants, of which tropospheric ozone is the main pollutant. Fossil fuel burning and deforestation combined with burning vegetation, burning the forests, contribute to smog formation. Remember, pollutants may be primary, active upon emission, or secondary, arising from primary pollutants undergoing physical or chemical change. Smog begins with primary pollutants, such as carbon monoxide, nitrogen oxides, and carbon dioxide. Under the influence of high levels of light, particularly some UV wavelengths, the primary pollutants are transformed into secondary pollutants, such as ozone. Nitrogen oxide is a primary pollutant, and ozone is a secondary pollutant transformed by high levels of light. NO2, nitrogen dioxide, is also a secondary pollutant. Here's an IB syllabus statement that digs in a bit deeper. State the primary pollutants from the combustion of fossil fuel, including carbon monoxide, carbon dioxide, black carbon, these are particulates, unburned hydrocarbons, oxides of nitrogen, and oxides of sulfur. Are you taking notes? Here is an outline of smog formation. Smog is a mixture of primary and secondary pollutants that form in the presence of UV radiation and the right meteorological conditions. More on these conditions later in the movie. Primary pollutants from vehicular emissions, fossil fuel combustion, coal burning, fossil fuel combustion, and deforestation in combination with the burning of vegetation interact with sunlight, UV particular, to form secondary pollutants such as ozone. Tropospheric ozone is one of the secondary pollutants of smog, and it is ozone that causes respiratory problems, irritated, watery eyes, and difficulty with breathing. Smog formation is a daily event that occurs in big cities where a lot of fossil fuel is being burned, and it occurs in regions with high sunshine and in regions where the air is trapped by geographical features such as mountains that surround the city. Primary pollutants are released in the morning during rush hour: nitrogen oxide, carbon monoxide, hydroxide, and reactive hydrocarbons. And these primary pollutants are exposed to high levels of sunshine as they remain trapped over the city over the course of the day. And by afternoon, the secondary pollutants, nitrogen dioxide, ozone, and PAN, which is a hydrocarbon, are formed. Here's a diagram that nicely displays the outline of smog formation. The primary pollutants in the morning include nitrogen monoxide, reactive hydrocarbons, and carbon monoxide. And then they're exposed to sunshine and transformed to secondary pollutants by afternoon, including nitrogen dioxide and ozone, and the hydrocarbon PAN that causes smog to have a brown color. The smog is pushed out of the city by the time the sun sets, and the process starts again with rush hour traffic the next morning. Here is the next relevant IB syllabus statement. Describe the formation of secondary pollutants, including the transformation of primary pollutants in the presence of sunlight and other chemicals already present in the atmosphere. Remember that sunshine, particularly UV wavelengths, are important catalysts in the formation of photochemical smog. This graph is also a nice outline of photochemical smog formation. Study this graph. Primary pollutants in the morning during rush hour, and then as the day passes exposed to sunshine, as the sun comes up higher overhead, and they're transformed to secondary pollutants, including ozone, by afternoon. Photochemical smog starts with two molecules emitted when cars burn fossil fuels. They are reactive hydrocarbons and hydroxide. The reactive hydrocarbons come from incompletely burned gasoline. These are the fuel vapors that you can smell when gasoline is pumped into the car. The hydroxide is very reactive, and together they initiate a series of reactions that result in the production of nitrogen dioxide, NO2, as a secondary pollutant. Now, you don't need to know anything on this slide except that NO2 is a secondary pollutant. NO2, under the influence of UV, ultimately results in ozone. Let's take a look. But here is detail that you need to take into your system. Describe the formation of tropospheric ozone as an example of a secondary pollutant. Nitrogen dioxide, under the influence of UV light, liberates a reactive oxygen atom that combines with a molecule of oxygen to form ozone, O3. Ozone, formed in the troposphere as a part of smog formation, is a secondary pollutant that causes respiratory problems in people and reduces the productivity of plants. One more time, here are the primary pollutants released during morning rush hour. You need to know that nitrogen oxide is a primary pollutant. And here are the secondary pollutants: ozone, nitrogen dioxide, and hydrocarbons, formed from the primary pollutants under the influence of UV radiation. This graph shows carbon monoxide levels over the course of the day. This graph shows how carbon monoxide peaks in the morning during rush hour. Carbon monoxide is a primary pollutant. Notice that levels of carbon monoxide are higher in the winter. That's because cold air is held nearer to the Earth's surface in the winter, and that's where carbon monoxide levels are measured. The effect of the cold air near the Earth's surface is called a temperature inversion. More on this later. This graph shows nitrogen dioxide over the course of the day, and the graph shows how nitrogen dioxide, a secondary pollutant, peaks late in the morning as a secondary pollutant formed following the exposure of the primary pollutants to light. Again, levels are slightly higher in the winter months when temperature inversions are more likely. Ozone is the dangerous secondary pollutant typical of smog conditions. Here's the relevant IB syllabus statement. Tropospheric ozone is an example of a secondary pollutant formed when oxygen molecules react with oxygen atoms that are released from nitrogen dioxide in the presence of sunlight. I've covered this material in previous slides. Remember, smog, including the ozone that's formed as a secondary pollutant in smog formation, is a tropospheric pollution problem in regions with high densities of people and the combustion of fossil fuels. But there's more. Stay tuned. Smog, and ozone as a secondary pollutant within smog, is a tropospheric pollution problem in regions with high densities of people and regions with high levels of sunshine, dry regions, desert regions. Often, cities with the worst smog problems are surrounded by mountains that prevent air from moving away. But there's more. Stay tuned. The conditions under which smog forms are detailed in this IB syllabus statement. Describe the conditions that influence the development of smog, including local topography, thermal inversions, climate, population density, and fossil fuel use. Before showing you images of each of the conditions mentioned in the previous slide, let me just state the four conditions again. High density of people and automobiles, fossil fuel use. High levels of sunshine, a dry climate, desert biome. Cities in a valley, mountains surrounding the city will trap pollutants. This is local topography. And temperature inversions, stable air, warm air over cold air because cold air is more dense and settles below the warm air. This is very stable and is called a temperature inversion. This is an image of Los Angeles, but imagine Mexico City, New Delhi, India, Beijing, China, and take note of the conditions for smog formation. high density of people, high use of fossil fuels because of cars and commuting. The city is ringed by mountains, and Los Angeles sits in a desert biome, thus high sunshine, photochemical smog. Smog formation occurs more readily when cities are located in a basin or a valley surrounded by mountains. The mountains hold the air, preventing the air from moving away. And the image here displays levels of carbon monoxide, a primary pollutant, being highest in the center of the basin, ringed by mountains. Smog formation requires high levels of sunshine. Dry climates, such as deserts, with high levels of sunshine, provide the best conditions for smog formation. A thermal inversion is a factor enhancing smog formation. Thermal inversion occurs when cold, dense air sinks below warm, less dense air. You can see cold air here and warm air here. If you think about what you know of the troposphere, warm air above cold air is not typical, but thermal inversions occur and occur often in dry climates. Thermal inversions prevent air from mixing, trapping the pollutants close to the ground level, facilitating the exposure of pollutants to the sun, thus enhancing smog formation. A thermal inversion can be clearly seen in this image of Los Angeles. The line of cold air beneath the warm air is clear. Thus, the polluted air is held close to the Earth's surface, and the mountains prevent air from being pushed out. Here's the IB syllabus statement on thermal inversions. Thermal inversions occur due to a lack of air movement when a layer of dense cool air is trapped beneath a layer of less dense warm air. This causes concentrations of air pollutants to build up near the ground instead of being dispersed by normal air movements. Here is Los Angeles. Notice the conditions for smog formation. Name 4. They can all be seen here. Here is Santiago, Chile. Notice the conditions for smog formation. Name 4. They can all be seen here. Here is Ulaanbaatar, Mongolia. Notice the conditions for smog formation. Name 4. They can all be seen here. Here is Mexico City. Notice the conditions for smog formation. Name 4. They can all be seen here. Once again, here are the conditions that favor smog formation. I'll let you study this slide on your own. So here is the next IB syllabus statement on tropospheric ozone and its effects on living things. Tropospheric ozone is highly reactive, damages plants, irritates eyes, creates respiratory illnesses, and damages fabrics, including rubber materials. Tropospheric ozone damages crops and forests, it irritates eyes, causes respiratory problems, increases susceptibility to infection, damages rubber and other fabrics. This graph displays relative crop yield against ozone concentration. As compared to 100% yield with no ozone, you can clearly see the negative effect of high levels of ozone on the relative yield of many crops: cotton, peanut, soybean, wheat, and corn. Ozone, tropospheric ozone, damages crops and forests, it irritates eyes, causes respiratory problems, increases susceptibility to infection, damages rubber and other fabrics. Ozone damages fabrics by making them more brittle, more likely to crack. Smog, including ozone, has negative effects on local economies. You can see in the graph the number of premature deaths in various countries across the world that occur due to particulate matter and ozone. Air pollution is likely to reduce global economic output by about $330 per person per year due to elevated health costs and work days lost to air pollution-related illness. Smog, including ozone, has negative effects on local economies. You can see in this graph the change in GDP due to air pollution seen in extra health costs and lower productivity in the workforce. The change is mostly negative. So that brings us to the last IB syllabus statement of the movie. Describe and evaluate pollution management strategies for reducing photochemical smog, including altering human activity to consume less fossil fuel, such as energy-efficient technologies, use of public transport, walking, or cycling, regulating and reducing pollutants at the point of emission through government regulation and taxation, using catalytic converters to clean the exhaust of primary pollutants from car exhaust, regulating fuel quality by governments, and adopting measures such as reforestation, regreening, and conservation areas to sequester carbon dioxide. The first strategy to reduce smog formation would be Strategy 1, altering human activity through education, incentives, and penalties, and using alternative technologies. Choosing energy-efficient technologies or choosing to change our behavior and use less energy would be the best strategy because fewer pollutants are released and it's the least expensive strategy. However, there are limitations in the efficiency of technologies, and human behavior is often difficult to change without incentives or good education. Carpooling and using public transport or bicycling would also reduce smog, but these forms of transportation are less convenient for workers and may reduce time on the job or reduce quality of life. Changing societal behaviors is not easy, but with incentives and law, Strategy 1 can be the most effective option for reducing environmental harm and lowering the cost of pollution. Alternative energy sources would reduce the effects of burning fossil fuels, including smog, but for the moment they are expensive and not practical in the transportation sector because most alternative energy forms produce electricity. Alternative energies reduce the burning of fossil fuels, thus reducing smog, but alternative energies need to be cheaper or their use needs to be mandated by law and enforced. Alternative energies produce electricity, which is a less practical form of energy for use in automobiles. Governments could regulate, reduce carbon monoxide and carbon dioxide emissions by putting a tax on carbon emissions. If they make it more expensive to burn fossil fuels, people would be less likely to burn fossil fuels. Reducing or regulating pollution at the point of emissions, Strategy 2, can be done with catalytic converters or smokestack scrubbers or filters. These forms of technology add cost to the prevention of pollution. Governments can regulate fuel quality. High-quality fuels are cleaner fuels, and they result in fewer primary pollutants. High-quality fuels are more expensive, and governments must impose fuel use standards. Governments can be slow to act, and governmental decisions are politically influenced, involving compromises. Reforestation, as you can see in this image, or regreening, or creating conservation areas would serve to sequester carbon dioxide, remove carbon dioxide from the air due to photosynthesis. Reforestation, regreening, or creating conservation areas would reduce air pollution. But these strategies are the third strategy and least effective strategy for pollution management because the harm of the pollutant has already been done and solutions can be expensive. We could sequester carbon dioxide underground. In other words, force carbon dioxide into deep storage, force its removal from the air to reduce its concentration in the atmosphere. Underground carbon sequestration is a type of geoengineering and is expensive, and the harm of the pollutant has already been done. Here's another look at this IB syllabus statement. I'll let you study this slide on your own, as I've already talked through the evaluation of all of the points made here in the slides previous to this one. Here's a summary of Strategy 1 pollution management solutions aimed at reducing smog. I'll let you study this slide on your own. Here's a second slide evaluating Strategy 2 and Strategy 3 solutions under the pollution management framework for reducing smog. Remember that Strategy 1, altering human behavior through education, incentives, and penalties, or using alternative technologies would be the most effective strategy because it reduces the pollution released in the first place and also is less costly. And that brings us to the end of IB ESS, Atmospheric Systems and Pollution Management, Part 6.